Did you know our Sun is 4.6 billion years old, or that its atmosphere is 300 times hotter than its surface, or that the Sun's mass accounts for 99.6% of our solar system's mass? Welcome to Science with Lou. Gazing into the cosmos, we see countless stars illuminating the sky. Among them, one star stands out: the Sun. Throughout history, it has inspired tales and legends. Now, with advanced technology, we explore the Sun's mysteries. Journeying into its fiery depths, we uncover captivating phenomena. Join me as we delve into the Sun's heart, using different wavelengths to reveal its secrets. Let's embark on a scientific exploration, not through physical space, but through the electromagnetic spectrum. Our target, the Sun, a colossal sphere of plasma, not static, but dynamically churning with immense energy. The sunlight we perceive, though inconceivably fast, painting a picture 8 minutes and 20 seconds old, masks a deeper truth. Within the Sun's core, a far older journey unfolds. Here, nuclear reactions birth photons, messengers of light, destined for our eyes. Yet their passage is arduous. Within the Sun's dense plasma, they encounter delays, deviations, and even temporary absorption, embarking on a circuitous trek that can span millennia. By the time these photons escape the Sun's surface, their age ranges from 10,000 to 170,000 years. Each ray, therefore, carries a silent tale of a Sun significantly different from the one we witness today. So, when you feel the Sun's warmth, remember its touch transcends the present. It is the echo of an ancient star, whispering stories of countless cosmic dawns. Starting our exploration akin to savoring a fruit, let's peel back the layers, commencing with the Sun's outermost atmospheric veil, the corona. Behold, this mesmerizing image captured by the Solar Dynamics Observatory, SDO, a NASA mission designed to decode solar intricacies affecting life and our technological systems. Through a lens of 19.3 nanometers, a wavelength delving into the extreme ultraviolet range, this image unveils the elevated expanse of the Sun's corona, glowing at a scorching 1 million Kelvin. Astonishingly, the corona occasionally graces the naked eye during rare occurrences, notably during a total solar eclipse, when the moon briefly obscures the central, brighter disk, revealing the corona's radiant aura. However, the detailed view rendered by the SDO surpasses this glimpse, offering scientists an invaluable tool for deeper study. Now let's delve deeper, peering just beneath the corona's surface, where temperatures soar to a striking 20 million Kelvin, unveiling intense, vivid spots denoting solar flares. Witness this footage from August 2022, capturing a bustling week of these colossal explosions that shower immense electromagnetic radiation into space. These flares, born from magnetic field distortions within the Sun's turbulent plasma, stand as both fearsome and captivating phenomena. Yet solar flares aren't the sole celestial theater emitting radiation. Behold the coronal holes, delineated by darker regions on the Sun. These enigmatic cavities warrant a closer inspection using extreme ultraviolet light, harboring their own captivating allure within the Sun's radiant tapestry. Coronal holes, regions within the Sun's outer layers hosting cooler and less dense plasma, boast magnetically open configurations. Unlike closed loops returning to the Sun's surface, their magnetic field lines extend outward across the solar system. These openings facilitate the escape of solar wind particles into space. When these winds interact with Earth's magnetosphere, the stunning dance of aurora lights illuminates the polar skies. The ultraviolet light provides an enhanced view of these captivating aspects of the sun's outer realms. There's an entire array of features to explore. Large, cool clouds of plasma suspended above the sun's surface, known as prominences, majestically rise from the sun's surface like glowing clouds, dwarfing our planet in scale and extending hundreds of thousands of kilometers into space. Though they can materialize in a day, stable prominences endure in the corona for months. Consider this spectacle: a prominence weaving its way out of the photosphere into the sun's atmosphere. Although the video is sped up, the magnitude of this phenomenon emphasizes how swiftly the sun's magnetic forces drive this colossal movement. Now here's an intriguing tidbit. The sun's atmosphere experiences rain. Not all charged plasma ejected into the corona ventures out into space. Some gets trapped, cools, and descends back to the sun's surface as a luminous rain, a stunning sight, but still searingly hot at millions of degrees. However, not all plasma gracefully descends back to the sun. Enter coronal mass ejections, CMEs, a dramatic display where tightly wound magnetic fields trigger massive eruptions of plasma into space. These eruptions, imaged through the SDO's lens at a 30 nanometer wavelength in the extreme ultraviolet spectrum, hold immense potential impact, posing threats to our satellites and electrical grids if Earth were to encounter a powerful one. Each of these structures imaged by the Solar Dynamics Observatory, SDO, corresponds to the extreme ultraviolet range, essential for timing the observation of these features, which exhibit variability tied to the sun's activity, fluctuating within an 11-year solar cycle. This cycle, often likened to the sun's mood swings or a cycle of highs and lows in the sun's activity, denotes an 11-year period of increased and decreased solar activity. During this time frame, the sun undergoes fluctuations in its magnetic activity, influencing the appearance and behavior of phenomena like coronal loops captured in extreme ultraviolet wavelengths. As fascinating as visible and ultraviolet light are, employing different non-visible light wavelengths unveils distinct facets of these solar features. Take a glance at these contrasting images of the sun's corona, illustrating how varying wavelengths offer unique insights into this celestial marvel. In this comparison of two images captured over the same period, we observe the sun's corona using two distinct wavelengths. The first image, portraying the tranquil corona at a color temperature of 600,000 Kelvin, showcases the presence of coronal loops, which are arched magnetic field lines filled with hot plasma above the sun's surface. In contrast, the second image, at a scorching 2 million Kelvin, unveils the significantly hotter active regions within the corona. This striking contrast underscores the necessity of employing diverse methodologies to scrutinize this stellar entity. What may initially seem a solitary solar occurrence can unfold as a convoluted, interconnected sequence of events. Venturing deeper into the sun's atmospheric layers, let's examine another image from the Solar Dynamics Observatory, this time focusing on the transition region. Nestled between the corona and the chromosphere, this region spans a mere 100 kilometers in thickness. Here, the sun's thermal temperature escalates dramatically from approximately 8,000 to a scorching 500,000 Kelvin. For comparison, the intensely hot lava from Hawaii's Kilauea volcano reaches 1,170 degrees Celsius or 1,443 Kelvin, significantly cooler than this transition region. At its upper end, the temperature exceeds 346 times that of the lower end, showcasing the immense thermal gradient. Delving further inward, we encounter the chromosphere, the sun's penultimate atmospheric layer, imaged using 170 nanometer ultraviolet light. This layer measures about 1,700 kilometers thick. Within the chromosphere lie captivating features known as spicules, tiny needles of fire shooting up from the sun's surface. These plasma jets surge upwards from the sun's surface at speeds up to 100 kilometers per second, nearly 282 times faster than the speed of sound, extending nearly 10 kilometers, surpassing the height of Mount Everest. Understanding these spicules puzzled scientists for a time, as the escape of magnetically charged particles from the sun's magnetic fields seemed implausible. However, in 2017, a detailed model investigation shed light on their origins. The discovery revealed that neutral particles previously emitted from solar models actually played a pivotal role. Once included, these neutral particles provided unexpected buoyancy to the magnetically charged particles, enabling their escape from the sun's plasma and the formation of spicules. Descending deeper into the sun's lower atmosphere, we arrive at the photosphere, the sun's visible surface, best observed using visible light. Although the photosphere's edge appears sharply defined from our vantage point, it's an illusion shaped by the sun's distance. The sun isn't solid. Its extreme heat prevents the existence of matter in solid, liquid, or gaseous states, leaving it predominantly as plasma, the fourth state of matter, constituting 99.9% of the universe. Plasma, akin to gases, comprises ionized atoms and free electrons. The photosphere, about 400 kilometers thick, represents the outermost layer. Contrary to the appearance of a fixed, solid boundary, it's a dynamic layer, and unfortunately, it's the deepest layer of the sun directly measurable by scientists. The dark patches or sunspots on the left side appear darker due to cooler temperatures, albeit still scorching, arise from strong magnetic fields, trapping heat beneath the photosphere, reducing convection in those zones. A connection emerges between sunspots and solar flares when comparing this visible light image to the previous extreme ultraviolet one taken simultaneously. Notably, solar flares and sunspots align, suggesting a correlation between the two phenomena. Delving closer, let's examine similar sunspots captured by the Swedish Solar Telescope, revealing the surrounding photosphere teeming with jagged-edged cells resembling ever-shifting lava. These solar granules, around 1,000 kilometers wide, populate the photosphere's surface, resembling the top layer of churning motions within the sun that transfer heat from its core to the surface called convection cells underneath, similar to boiling water. Bright regions within each granule signify unimaginably hot fluid rising from the sun's upper layers to the surface, spreading outward before cooling and returning inward along the dark boundaries. This cyclic process mirrors Earth's mantle convection driving plate tectonics. Despite each granule's brief lifespan of about 20 minutes on average, the fluid within these cells races at supersonic speeds, exceeding 7 kilometers per second, creating surface waves akin to sonic booms. Remarkably, these granules, also visible in the full disk view, create the granular appearance in the image, not a technical artifact. The graininess mirrors the photosphere's dynamic cells, offering a glimpse into the sun's perpetual activity. What an incredible journey into the heart of our celestial neighbor. Unfortunately, our expedition halts here, the sun's deeper layers veiled from our current imaging capabilities. Much of what lies beyond this photospheric layer remains veiled in mystery, an enigmatic territory waiting to be unveiled by future advancements. Nevertheless, the profound significance of employing varied light spectra in our solar study emerges vividly. These diverse wavelengths unveil exploding solar flares, expansive coronal holes, undulating spicules, enigmatic sunspots, and the ever-shifting solar cells, introducing us to a vibrant panorama of solar activity. The Sun pulsates with dynamic phenomena, many of which would remain unseen without these ingenious imaging techniques. Perhaps one day, we'll pioneer methods to delve deeper into the Sun's realms, utilizing innovations beyond our current imagination, reminiscent of the vast technological leaps from ancient times to our present tools. Yet the awareness of vast unseen realms in our universe, coupled with our capacity to uncover them, ignites an exhilarating curiosity. Who knows what other cosmic marvels await our discovery, hidden in the cosmic tapestry, yearning to reveal their secrets? Make sure to leave a like on this video, subscribe to the channel, and ring the notification bell so you don't miss out on more discoveries. See you on the next one.